So just over a year ago now, at the end of one of my other videos, I said this. I should really build some rocket engines that run like this. I might get round to that. So I did actually get around to doing this said creation of a rocket, and I'd like to explain exactly what I'm meaning by this. I'm getting the bottle of hydrogen and oxygen idea that I had previously used in the video I just showed, and adding on to the end a nozzle to adapt the gases going out in the same way that rocket engines do here. If you can see on the footage I have up at the moment, this is footage of the bottom of the space shuttle, and you can see two of the main big engine bells on the bottom of the space shuttle. So effectively what I've done is I've created a screw-on version of one of these engine bells that could attach onto a bottle in order to mimic, and basically for just me to play around and study for myself exactly how these things work. So the basic premise behind this is that you have the hot gases being combusted in the engine, and this creates something that is at very high temperature and very high pressure. But what you want for a rocket launch, of course, is you want high velocity exhaust gases. Because the rocket equation, I'll probably put this on screen now, tells you how much delta V your rocket will get, which is effectively a measure of how much it can change its speed, which in rocketry and orbital mechanics is the thing that really matters about a particular thing. And that is dependent on the exit velocity of the gases. Now there is a trick. This was originally developed for steam turbines, actually, called the de Laval nozzle, that allows you to accelerate the exit gases much faster. And effectively the way this works is you have a very narrow throat to the nozzle where it exits the combustion chamber, where it exits at an incredibly high temperature and pressure. You then expand it at about a 15-degree cone, and this expansion causes the gas to cool and lose pressure, because of course if you have the same volume of gas you have the same fluid flow effectively, but you're putting it through a larger area, the cross-sectional area of what you're putting it through increases, then the pressure is going to drop. However, the energy of this is remaining the same, so the trade-off is that the velocity of the particles of this gas ends up increasing, which means the speed of what you're throwing out the bottom increases. Of course, that means the kinetic energy of what you're throwing out the bottom increases, which of course is helpful because kinetic energy and the reaction force is exactly what you want in the rocket. So as you can see here, it's leaving the solid fuel and it's expanding ever so slightly, because that means it's coming out still at slightly higher than the surrounding atmospheric pressure. Later you will see that this is effectively what the solid fuel booster is, what my bottle and hydrogen design ends up doing. Here I have the nozzle design I came up with. The idea is it's just a de Laval nozzle here, and then a screw adapter that can fit onto a Coke bottle on this side. The nozzle was made by me and the university computers in SolidWorks, and the adapter was found on a website called Thingiverse. I'll probably leave links in the description to the website because it really is quite useful, as well as hopefully some form of download link that would allow you to have this design for yourself, because it is quite useful. Or, well, it is useful if you have a 3D printer. I don't know what you guys have. So yeah, it's a fairly simple design. You'd have the bottle on here, which would have any form of fuel into it. You can then see the sort of throat there where it constricts it, and then of course the gas is expanded at the back at what is approximately a 15-degree cone. So yeah, I had that printed out on the university 3D printers. It's wonderful thing to occasionally have access to fancy technology that I wouldn't be able to have otherwise. Although it does absolutely nuke my upload regularity. Sorry about that, guys. So yeah, I had this printed out, and then I did a series of tests over Christmas and the last few days before I uploaded this. And I'll cut to those. With the electrolysis having been done for a suitable amount of time, I now have a full bottle of hopefully hydroxy gas inside this. I'm going to light to ignite it with. Hold it up. Well then, that was more powerful than I expected it to be. Okay, so I have my filled bottle, I have my lighter, and I will perform the test of the engine. I am wearing IFRIC to protect my ears. As soon as my lighter decides to work. So as you can see here, the gases are entering the nozzle, they're going all the way through it, glowing rather nicely, and then they're expanding further once they reach the end of the nozzle. This is because the nozzle is what's known as under-expanded, meaning that they're still at a higher pressure than the surrounding atmosphere when they leave. This means that it's not operating as efficiently as is optimal, but often with rockets you do have to make a compromise with these. For example, these nozzles are always adapted for the height and atmospheric pressure that they are designed to operate at. A good example of this would be the Falcon 9 rocket that has several small engine bells for the first stage optimized to work at atmospheric pressures, and then one huge engine bell on the second stage engine that is optimized to work in a vacuum, and therefore of course the pressure of the outputting gases is more efficient when that pressure is much lower. What I tried to do to change my nozzle here was to block off the throat slightly. The idea behind this was that that would increase the expansion ratio between the throat and the exit of the nozzle, and therefore that would decrease the pressure of the gases exiting even further than they already were by this design. However, it went slightly differently than that, as you're about to see. And at the other end of the bottle, I have installed a new system of lighting this to save me just sticking a lighter at the end and hoping for the best, because of course with the smaller hole it'll be even harder for the flame to get through the nozzle and into the main chamber. So I have a very basic electric igniter connected to a set of wires that then go inside and can generate a spark inside the chamber. All in all, this should make it much easier. Okay, so it's all fueled. The electric igniter is in place. So I'm going to grip it tightly so it doesn't go flying, but definitely make sure that that my head is not above it in case it does. Grip it. Ready for firing. All ready. Well. Ah well. So in the aftermath of that last test, the electric igniter worked exactly as intended, and that's all fine, but the nozzle is less fine. So with my engine broken into quite a few pieces, looks like I'm going to need a new one, so away with that. And what can I make a new nozzle out of? I don't have access to 3D printers anymore, so I don't know. So what about a 2 litre bottle? So you've got this, cut off the screw bit, we don't really need that. And a de Laval nozzle performs optimally when it's about a 15-degree cone, so I've got a piece of cardboard that just allows me to check the size that I want. So, I don't know, sort of fold it around, get it as far in as I can on this, to make the smallest end possible. Also make the other end as wide as possible. Fold it round a little bit. Something like that. It's not bad. To glue that, it might work. Now I have my backup replacement nozzle. It's made very simply of a pen nib with some supports on it, a slightly smaller roll made from a small bottle, and the big end made from the big 2-litre bottle. There's a ring on the end. This purpose is to try and keep this vaguely in a circular shape, because it likes warping itself into an oval, and it's still not quite circular, but it's close enough. So, as usual, fill it with water, stick it on the Coke bottle, and start fueling it. Okay, test with the new custom nozzle. Just going to get it out. I've been filling it. Move over into where the cameras can see. Begin testing in 3, 2, 1. So I have this frame here from the video. I think it's quite interesting because I think it's the best one of the frames that you can actually see the shockwave. It's times like these that I wish I had a high-speed camera, but I can't afford one, so I just have to look through each individual frame of the footage from my camera. I think it's about 30 frames per second, something like that, and see which one's the most interesting ones to comment on. But I think this really is one of the best ones because you can just about make out the shockwave of the exhaust gases going out the bottom of this. So yeah, I hope you enjoyed these rocket nozzles. I am thinking of continuing with this. At some point I'd want to integrate it into maybe a design that could launch itself into the air. But the problem, of course, with this is twofold. One, if you're launching something like this made of a bottle, you'll need a large area so that you can actually catch the thing when it comes back down, so that you're not just launching random things into the air and forgetting about them, which wouldn't be the best thing to do. And also there's the fact that because all of these things are very prone to leaking and all such, I've been fueling them and setting them off immediately after, which again I wouldn't be able to transport my power supply and such to any place that would have wide enough open spaces for me to be able to launch. All in all, this was mostly just to explore the theory of rocket engines and sort of prove that, yeah, whilst you can 3D print one, it's almost as effective just to glue together some bits of broken bottle, as long as you don't want it to handle sustained high temperature flow of hydrogen and oxygen. I'm pretty sure if this these burns lasted longer than the sort of quarter of a second that they do, then the plastic wouldn't hold in the slightest. So hope you all enjoyed, and I'll see you whenever I get round to making another video. Hopefully it won't be as long a wait, but I have exams, so no promises.